Welcome to all students. I am Professor S.S. Iyer. Today we discuss about 2D problem in finite element analysis. In finite element analysis, the 2D problem, general formula for the stiffness matrix, displacement u oblique v in a plane element are interpolated from nodal displacement ui vi using shape functions ni as follows. So uv is equal to n0 0 n2 0 0 n1 0 n2 u1 v1 u2 v2 or u is equal to nd, where n is the shape function matrix, u is the displacement vector and d is the nodal displacement vector. Here we have assumed that u depends on the nodal values of u only and v on nodal values of v only. Most commonly employed 2D elements are linear or quadratic triangles and quadrilaterals. In constant strain triangles CST or TT, this is the simplest 2D element, which is also called linear triangular element. So the diagram XY, and in this diagram 1, 2, 3, x1, y1, x2, y2, x3, y3. For this element, we have 3 nodes at these verticals of the triangles, which are numbered around the element in the counterclockwise direction. Each node has 2 degrees of freedom, can move in the x and y directions. The displacement u and v are assumed to be linear functions within the element, that is u is equal to b1 plus b2x plus b3y. V is equal to b4 plus b5x plus b6y, where bi is equal to I is equal to 1 to 6 are constant. From these, the strains are found to be epsilon x is equal to b2, epsilon y is equal to b6, and zeta xy, gamma xy is equal to b3 plus b5, which are constant throughout the element. The displacement should satisfy the following 6 equations. u1 is equal to b1 plus b2x1 plus b3y1, u2 is equal to b1 plus b2x2 plus b3y2, v3 is equal to b4 plus b5x3 plus b6y3. Solving these equations, we can find the coefficients b1, b2 and b6 in terms of nodal displacement and coordinates. The displacement can be expressed as uv is equal to n1 0, n2 0, n3 0, 0 n1 0, n2 0, n3, u1 v1 u2 v2 u3 v3. The shape functions for linear functions in x and y are n1 is equal to 1 upon 2a x2 y3 minus x3 y2 plus y2 minus y3 into x plus x3 minus x2 into y. n2 is equal to 1 upon 2a in bracket x3 y1 minus x1 y3 plus y3 minus y1 into x plus x1 minus x3 into y. n3 is equal to 1 upon 2a x1 y2 minus x2 y1 plus y1 minus y2 into x plus x2 minus x1 y, and a is equal to 1 by 2 determinant of 1 x1 y1 1 x2 y2 1 x3 y3 is the area of the triangle. The strain displacement relation are written as epsilon x epsilon y gamma xy, that is equal to b into d, 1 upon 2a y2 3 0 y3 1 0 y1 2 0, where xij is equal to xi minus xj, yij is equal to yi minus yj, ij is equal to 1 2 3. Again we see constant strain within the element. From stress strain relation we see the stress obtained using the CST element are also constant. The element stiffness matrix for the CST element K is equal to integral V b raised to t e b into dv is equal to t into a b raised to t e b, in which t is the thickness of the element. Notice that K for CST is a 6 by 6 symmetric matrix. In natural coordinates, this is the diagram. there is AB coordinates, there is zeta 1, zeta A, zeta equal to 0, n is equal to 0, efficiency 0, this is the efficiency 1B 0, where we introduce the natural coordinate system. We introduce the natural coordinate system zeta and r on the triangle, then the shape functions can be represented by simply by n1 is equal to zeta, n3 is equal to 1 minus zeta minus efficiency. So it is noticed that n1 plus n2 plus n3 is equal to 1, which ensures that the rigid body translation is represented by the chosen shape functions. Also it is as it is 1D case, n1 is equal to 1 0 at node I at the other nodes and varies linearly within the element. The plot for shape function n1 is shown in the following figure. n2 and n3 have similar features. So x1 is equal to n1 x1 plus n2 x2 plus n3 x3, y is equal to n1 y1 plus n2 y2 plus n3 y3, where xij equal to xi minus xj and yj equal to y minus j yj, where ij is equal to 1, 2, 3 as defined earlier. Displacement u or v on the element can be viewed as a function of x, y. Using the chain rule for derivatives we have, this is the equation. Now, applications of the CST elements is used in areas where the strain gradient is small, used in mesh transition areas, fine mesh to coarse mesh, avoid using CST in stress concentration or other crucial areas in the structure such as edges of holes and corners. Recommended for quick and preliminary FE analysis of 2D problems. So, thanks all of you.